Right guys, just want to do a quick little video here in relation to radioactivity. So this is chapter 8 in our textbook. So we'll get straight into it. So the founders, I suppose, of radioactivity was Henry Becquerel. And then you obviously had Pierre and Marie Curie. So just have a little bit of history about them. Generally, as regards those people, could be a short question in question 4 about them. Okay, so and also maybe possibly in question 5 they can do a little section on radioactivity as well. So it does pop up as a main, or it could be a question 10 or 11. That's kind of where the areas you're going to see radioactivity popping up. So the Marie Curie was awarded the Nobel Prize in Physics. She also received the Nobel Prize in Chemistry as well. In 1903 for her discoveries of radium and polonium. So just look in the chapter, it'll go through a bit about them. You can read through that. That's stuff you can find yourself. To detect radiation, we use a thing called a Geiger-Muller tube. So just be aware of what that is. And again, that's dealt with in the sorry about that. That's dealt with in the chapter as well. Right, so have a quick read of that. So then we have 3 different types of radioactivity. So we have alpha particles, that should be particles, we have beta particles, and we have gamma radiation. So in the case of alpha and beta particles, you have physical particles being spontaneously emitted from the nuclei of unstable atoms, and then radiation is actually giving off electromagnetic waves from the nucleus of the atom. Okay, so we look first of all at alpha particles. So basically, an alpha particle is a helium nucleus. Okay, so if we look at our periodic table and we see helium, which is here, right? So you can see there it's 4, 2. Okay, so its atomic number is 2, its mass number is 4. What that means is its atomic number tells you the number of protons, which is 2, the number of electrons, which is 2, and then the mass number tells you protons and neutrons, so it also has 4 minus 2, 2 neutrons. So helium atom has 2 electrons, 2 protons, 2 neutrons. If you were to draw it, what you'd get is, let's go down. Of course, set up the rubber. If you draw it, you would have a proton, neutron, a neutron. They'd be in your nucleus, and then orbiting, you would have 2 electrons. That is a helium atom. Okay, what an alpha particle is literally a helium nucleus. So that is an alpha particle: 2 protons and 2 neutrons. Okay, that's the first thing. Then beta radiation. So actually we'll talk about alpha particles first, or alpha particle for a second. So alpha particles consist of a stream of positive charged particles. So they're deflected towards negative charged plate. Now why are they positively charged? Well, let's look back at our little diagram again. You have 2 protons and you have 2 neutrons. Remember, neutrons have neutral charges, protons have positive charges. So there's 2 pluses and there's 2 neutrals. So therefore the overall charge on this is positive. So an alpha particle is a positively charged particle. That's why it'll be attracted towards a negatively charged plate, and it'll be deflected or repelled away from a positively charged plate. So we said 2 protons, 2 neutrons. They have low penetrating power and are stopped by a few centimeters of air or sheet of paper. So basically, because of their size, their ability to penetrate through things is quite small. Okay, so we'll find that alpha particles have the least penetrating ability, and as you move to beta particles, they are more penetrating, and the most penetrating will be gamma radiation. Okay, so it works that way. And the example of where you'll find alpha particles would be in American 241, which is found in smoke detectors. Okay, beta particles then are slightly different. Okay, they're basically electrons. Okay, so a beta particle is formed when a neutron is changed into a proton and electron. So when we talk about radioactivity, definition up there for it. So the radioactivity here is the emission of alpha, beta, or gamma radiation from the nucleus of unstable atoms. So basically, an alpha particles are given off. That's the form of radiation. It's spontaneously just given off. Okay, so it gives off a helium nucleus. Okay, now that will systemically change the actual atom itself, which we'll look at as well in a second as regards nuclear reactions. In beta particles, what's happening is one of the neutrons in the atom, in the nucleus of the atom, spontaneously breaks up. And when it breaks up, it produces two things. It produces a proton and an electron. Okay? So, if we go back here, we're saying beta particles will be electrons. A beta particle is formed when a neutron is changed into a proton and an electron. Now, if we look back at a little diagram, what happens is, here's radium, okay? Its mass number is 228 and its atomic number is 88. That means it has 88 protons, and 228 minus 88 is 150 neutrons. So there's 150 neutrons in here, and there's 88 protons, okay? If this undergoes beta radiation or particles breaking up, what happens is one of the neutrons gets converted into a proton and electron. The electron is emitted, and then the proton stays in the nucleus. Okay. Now this number here, this atomic number, tells us the number of protons in the atom. So currently radium has 88 protons, and we said 150 neutrons. If one of the neutrons changes, technically your mass number goes down to 227 because the neutron is gone. But then it converts it back into a proton, so it goes back up to 228. So the mass number remains the same, remains at 228. However, because you now have a neutron turning into a proton, the atomic number will increase by 1 to 89. Okay? So, that is what happens in beta decay. In alpha decay, which we touched on this before, you have your parent nucleus here, which is uranium. Okay? Now, if we look at this maybe from the point of view from the periodic table this time, here's uranium down here. Okay? So, its atomic number is 92. So, it has 92 protons. If it decays and gives off an alpha particle, remember, it is giving off 2 protons and 2 neutrons. Okay? So what will happen is the 92, which is the number of protons, and because it's giving off 2 protons, will turn into 90. So it'll actually change from uranium into thorium. Okay? And the atomic number in this instance, sorry, let's go back to the PowerPoint. The atomic number was the mass number was 235, so it's 92, 235. It'll turn into 90, and then because it's losing 2 protons and 2 neutrons, it's losing 4 parts of the overall mass number, so it goes to thorium 231. So that's what alpha particle breakup looks like, and that's what beta particle breakup looks like. Okay, in both alpha and beta particles, when they break up using both alpha and beta particles, you have atoms changing into new atoms, always. Okay, the way to look at it, I suppose, is in the case of alpha radiation or particles given off, your atomic number is going down by 2 and your mass number is going down by 4. In the case of beta particle breakup, what's actually happening is the mass number remains the same, so 228, but the atomic number goes up by 1. Remember, that's because a neutron is changing into a proton with the electron emitted. Okay. The last type of radiation then is gamma radiation. So this is radiation. This isn't a particle. So this is a substance giving off radiation. It is the most penetrative type of energy. It is high energy electromagnetic radiation of a very short wavelength. Okay. And it's very, very dangerous. Cobalt-60 gives off gamma radiation used to kill cancerous cells. So radiotherapy for cancer would be an example of gamma radiation. Okay. Be aware of this, the differences between the 3 different types of particles. Okay, so their nature. Alpha particles are positive, beta particles, put in touch with it, they're negative, and gamma particles are electromagnetic, so they're neither positive nor negative. And then their penetrating power, alpha particles low penetrating power, beta particles above 5 moles of aluminium, and gamma radiation needs lead in order to stop it. Okay, and that's just a diagram there to kind of illustrate that idea. Okay. Now, just a thing on nuclear reactions, which we'll look at as well. Oftentimes they'll tell you that something breaks up by alpha particles, or something breaks up by beta particles. Okay, so say take a 24195, right? So just forget you seen what I had up there, right? So a 24195. Now, oftentimes they put the mass number on top here on the right in this, and I'll just rewrite that again. Sorry. AM, so 2, 4, 195 AM. And you're told that this breaks up by alpha particles or alpha radiation, and you are asked to show the nuclear reaction. So you know that it is going to give off a helium atom because that is an alpha particle. So what you then do is you say, right, well, that's going to give me my helium has the mass number 4. That's going to be 237, and then 2 is 93. Now the 93 is the key number because that is going to dictate what the atom is. So go to 93, which is neptunium, which is Np. So I get, Np. And that is how I write the nuclear reaction for that. Okay? If you were told carbon, so 14,6 carbon, that breaks up and it's giving you beta particle. Now beta particles are normally written like this. I want to go down there. Sorry. So 0 B, something like that. Okay, that's your beta particle. Right? Remember, what's happening here is that the mass number will remain the same because neutron turns into a proton. That keeps the same. But now we're going to get an extra proton because one of the neutrons is turned into a proton. So it's going to be 7. If you go to periodic table, 7 is obviously nitrogen. So N. Okay? So you have to be able to write nuclear reactions for the alpha particles and the beta particles. Alright? And lastly then, I think on this, just make sure I have everything. So there's our nuclear reactions. The last thing then is the idea of half-life. Okay, so the half-life of an element is the time taken for half of the nuclei in any given sample to decay. Alright? The shorter the half-life, the more radioactive a substance is. Okay? So you might find something has a half-life of, we'll say, 30 minutes. Okay? What that means is, so if you have 100 atoms of something, after 30 minutes, half of them will remain. Okay, so if you have uranium and it just says 30-minute half-life, that means in, maybe illustrate this if I can, hold on time here, 15 minutes. Okay, so 2 minutes left. So, if you think of half-life and you have uranium and you have 100 atoms, and we're told the half-life is 30 minutes. What that means is after 30 minutes you will have 50 atoms. Then after 60 minutes you will have 25 atoms, half of the previous. Then 90 minutes you will have 12.5 or part thereof atoms, and so on and so forth. So we've seen with the coronavirus currently, we've a lot of these exponential curves this way. Half-life is a bit like this way. You start off with 100 atoms here and it goes that way. Okay? Now, the higher, as I said, the half-life, the more radioactive it is, and the longer the half-life, the less radioactive it is. You can have substances like carbon-14 and carbon-12. If you use it for radioactive dating, the half-life is very, very high. Okay, so that's why we're able to date older things or archaeological things as well. So guys, I'm just kind of up because the clock here, I kind of keep that 15 minutes. But basically, that is radioactivity. If you have any questions around this, ask me. What I'm going to do tonight is I'm going to give you the questions 8.1 to 8.4 at the end of this chapter, and I want you to work through them. And tomorrow then I'll bang out a Leaving Cert worksheet with some Leaving Cert questions based on this stuff. Okay guys, I hope that will help. And again, as I said, if you have any questions on this, anything you're not understanding, maybe the nuclear reactions or that kind of stuff, jot it down, let me know, and I can chat to you on Friday about it. But try and let me know before Friday so I can kind of link with it. Okay guys, take